The Milky Way is on a collision course with Andromeda. These two galaxies are going to merge. It's going to reshape our whole corner of the universe. Edwin Hubble proved galaxies were moving apart. He'd be surprised to learn our nearest large neighbor is actually coming toward us. This will change how you see our place in the cosmos and the nature of time. We're going to see how this event is both inevitable and peaceful, and we'll trace what happens to our solar system in that future galaxy to know the future of your own home in that kind of detail. Think of them as two great cities of light, separated by an ocean of emptiness. Our home is the Milky Way, a grand spiral. We live out in one of its arms, and from here we see that band of stars across the night sky. A river of ancient light. This galaxy has maybe 400 billion stars, vast clouds of gas and dust where new stars form. At its center, there's a supermassive black hole. Sagittarius, a star, it holds a quiet gravitational sway, but the real bulk of the galaxy, the reason it spins as one thing, is something we can't see at all. This brings us to Vera Rubin, an astronomer. She studied how stars orbit at the very edges of spiral galaxies, and she found something strange. Those stars were moving too fast. Way too fast. Based on all the visible matter, those outer stars should have been flung out into space. They weren't. The only explanation was that each galaxy sits inside an immense, invisible sphere of mass. A halo of something that has gravity but gives off no light. We call that dark matter. It's the hidden framework, the gravitational glue that holds the galactic city together. For the Milky Way, this dark halo is the true edge of its influence, a sphere of unseen weight stretching far beyond the last visible star. Now look toward Andromeda on a clear night. That faint, fuzzy patch, that's the light of our neighbor, M31. That light has been traveling for 2.5 million years to reach you. It's a spiral galaxy like ours, but bigger. Andromeda has about 1 trillion stars. It's the dominant giant in our local group. It also has a central supermassive black hole. And it's also shrouded in a halo of dark matter, an even more massive one. For a long time, we saw it as a static island, a landmark in the sky, but the discovery of dark matter changed that. These vast halos aren't just decoration. They're the engines of destiny. Their gravitational reach is so immense that the space between our galaxy and Andromeda isn't really empty. It's filled with the invisible, pulling tendrils of their dark matter. They're already drawing them together across that gulf. So to understand their future collision, you have to see them differently. Not just as collections of stars, but as these immense gravitational beings, whose unseen bodies are already touching that faint patch of light, Andromeda. For a long time, it was just a nebula. Astronomers thought it was a cloud inside our own galaxy. Then there was this big debate. Were these spiral shapes part of the Milky Way, or were they their own separate island universes? The answer would change everything about where we are. It started with a measurement of light. An astronomer, Vesto Slipher, he used a spectrograph on Andromeda in the early 1900s. He broke the light into a spectrum, and he saw the lines were shifted toward blue, which meant this nebula was moving toward us. That was the first clue. A single point of data, a hint of a future collision, but it was more complicated than that. Later, Edwin Hubble used the big telescope at Mount Wilson. He found individual stars in Andromeda that proved it was its own galaxy, an island universe. He also showed most galaxies are redshifted, moving away as the universe expands. So why was our closest large neighbor coming closer, showing blue shift? The motion we see is a combination. The expansion of the universe is trying to pull Andromeda away. But the local gravity, the pull between the Milky Way and Andromeda and all their dark matter, is stronger. It's a tug of war across millions of light years. And gravity is winning. For decades, the exact path was unclear. The sun's own motion around the galaxy center confused the measurements. We needed a view from outside that confusion. That clarity came from the Hubble Space Telescope. No atmosphere to blur the view. In 2012, after years of work, a team made a definitive measurement. They didn't just look at the galaxy's overall light. They tracked the motions of individual stars inside Andromeda over time, like watching a distant crowd and seeing how one person moves relative to another. Their study concluded Andromeda is on a direct course. A head-on collision is inevitable. That wasn't speculation. It was a forecast based on the precise laws of motion written across the sky. So the story of this discovery is a human story. It goes from early debates about nebulae to that first hint of blue shift to a space telescope patiently gathering data to confirm our fate. We went from not knowing what these spirals were to understanding our galaxy is living on borrowed time, caught in a slow, inescapable dance with a neighbor. Gravity is quiet, it's patient, it built everything we see. It holds planets in orbit, it keeps your feet on the ground, and across 2.5 million light years, it's pulling two galaxies together. An embrace that will last for billions of years. To get the scale of it, picture two dancers on a vast, frictionless floor. They're facing each other, but they're far apart. They aren't running, they aren't leaping, they just start to move, drawn by an invisible tether. Their steps are slow at first, almost impossible to see. But the pull gets stronger, their paths curve inward, the space between them closes, not in a rush but with a stately, inevitable grace. That's the dance of the Milky Way and Andromeda. The music is gravity, the rhythm is set by mass, an unimaginable amount of mass. The stars and gas we see, they're spectacular, but they're just decoration. Luminous decoration on a much more massive framework. The real weight of each galaxy is in its halo of dark matter. This invisible stuff forms a deep, spherical well around each galaxy. A pit in the fabric of space-time, so the galaxies aren't floating in empty space. They're each sitting in their own immense well, and those wells are starting to overlap. To merge even now, one cosmologist said it like this: this isn't a chance encounter in a vast, empty universe. It's a foregone conclusion, because we're in a relatively dense neighborhood. A collection of galaxies called the local group. In this group, the Milky Way and Andromeda are the two giants. All the other, smaller galaxies are like satellites. Caught in their gravitational sway, the combined pull of all that mass concentrated in our corner of the cosmos, it sealed the fate of the two largest members. They've been falling toward each other for billions of years already. Nothing can stop it. There's no force that can countermand gravity over those distances, over those timescales. So when we look at that faint smudge of Andromeda, we're not looking at a distant, unrelated island. We're looking at our future partner. In a cosmic merger, already caught in the same inescapable pull that makes an apple fall to Earth. The collision starts 4 billion years from now. To get what that means, you have to step outside of human time. Our lives, our histories, our whole species, that's thousands of years, maybe millions, but the universe runs on a different clock. Its second hand moves across hundreds of millions of years. One way to see it is to take the whole history of the universe, all 13.8 billion years, and shrink it down into a single calendar year. The Big Bang happens at midnight on January 1st. Everything starts there. In that cosmic year, our solar system doesn't form until early September. Life on Earth shows up in late September. The dinosaurs appear around Christmas Day, and they go extinct on December 30th. All of human history, from the first cities to right now, That's just the last few seconds before midnight on December 31st. So where does the Andromeda collision happen? It happens in the future, way beyond our little calendar. It's an event for the next year and the year after that. This timescale is so huge it can feel meaningless, but it's the real rhythm of galaxies. Think of it like this: the whole story of complex life on Earth, from the first creatures with backbones to everything we see now, that took about 500 million years. That's 1/8 of the time we have to wait just for Andromeda's first close pass. Our galaxy has more time ahead of it before this merger than all of animal evolution that's already happened. That changes the event. It's not a catastrophe, it's a process, it's not a crash. It's a slow-motion ballet choreographed by gravity, where every single step takes tens of millions of years. When we say the galaxies will merge, we're talking about a sequence of passes, gentle tugs, that will eventually weave them into one. So what's Earth like in 4 billion years? Will humanity even be here? We can't know. Our sun will still be shining, but it'll be growing brighter. The planet will be a very different place. All of human civilization is a fleeting spark next to the deep, slow currents of cosmic change. This perspective is humbling. It takes away any immediate fear and replaces it with awe. We're seeing, from our point in time, the announcement of a future so distant it challenges what the future even means. This grand timeline sets the stage for the specific phases of the dance. That smudge of Andromeda in the sky, it's faint, a fuzzy patch. You need a dark night to see it. But over billions of years, it will start to grow, not fast, but if you could watch, you'd see it swell. That tiny blob becomes a distinct shape, then a tilted spiral filling more of the sky. This is the first act, the long approach, the two galaxies falling toward each other. For eons, it's almost silent, but when they close to a few 100,000 light-years apart, their gravity becomes impossible to ignore. They're not solid, they're collections of stars, gas, dark matter, loosely bound, and as they near, the pull isn't even. The side of the Milky Way facing Andromeda feels a stronger tug. The side facing away feels less. That difference is a tidal force, like the moon and the ocean tides, but galactic. These forces start to work. They stretch the flat spiral disks of both galaxies. In simulations, you can watch it. The outer arms respond first. They're pulled outward into long, streaming arcs, stars and gas. It looks like each galaxy is reaching out an arm. These aren't collisions, they're distortions. The galaxies are beginning to dance long before they touch, and in those stretched arms, something gets triggered. All that gas and dust, jostled and compressed, collapses under its own weight. It ignites. This phase sparks a fireworks display, new star formation. Vast blue-white stellar nurseries light up along the arms. For a time, both galaxies become more brilliant, alive with new suns, a galactic renaissance driven by the gentle stress of a distant partner. So the first sign isn't destruction, it's creation, a reshaping. The stately spirals we know start to lose their form, warped and stretched in a slow-motion tug of war. This phase alone lasts hundreds of millions of years, a prelude, showing that even a collision begins with a patient distortion, gravity weaving two galaxies together from a vast distance. Those beautiful, distorted arms of stars, they're just the surface. They're following a script written by something far more massive and completely unseen. The real architect of this whole merger, the thing that sealed our fate, that will choreograph every single step, is dark matter. So you have to think of the two galaxies differently. Not as collections of stars. Picture two vast, invisible spheres like a strange, dense fog. This fog has gravity, but it doesn't glow. It doesn't reflect light. We can't touch it. We only know it's there because of how it pulls on the things we can see. And inside each of these immense, foggy spheres, there's a tiny, sparkling cloud. That cloud is all the stars, the gas, the planets. The luminous galaxy we see is just a small, bright ornament at the heart of a much larger, invisible body. That's the reality. The dark matter halo around the Milky Way is maybe 10 times more massive than all its visible stuff. For Andromeda, it's even larger. So when we talk about these two galaxies approaching, the first things to touch aren't the stars. They're these colossal halos of dark matter. They begin to overlap, to merge long before the starry disks get close. It's like two people walking toward each other through a thick fog. Their personal clouds of fog mingle first. They swirl together, influencing their path long before they ever shake hands. This interaction sets the rules. The dark matter provides the overwhelming gravitational pull. It accelerates the galaxies toward each other. It dictates the angle of their approach. It determines how they'll spin and twist during that first graceful pass. Physicists running supercomputer simulations of the merger, they found they couldn't get it right, not by only modeling stars and gas. The results looked nothing like what we observe in other merging galaxies. Only when they poured these vast, invisible halos of dark matter into their digital universe did the simulation snap into focus. The predicted dance finally matched the real one. And that reveals something, a profound, humbling truth about the cosmos. The largest structures, the grandest events, are orchestrated by a substance we cannot see. We cannot touch, we do not fully understand it. Our entire galaxy, every star we cherish at night, is just a passenger riding within a shadowy framework. A framework that guides its destiny across billions of years. We are living inside a mystery, watching its consequences unfold in the slow motion of celestial light. 4 billion years from now, the approach finally ends. The galaxies come close for the first time. They're stretched, distorted. It's not a direct collision. It's more like two huge flocks of birds swirling past each other. A near miss, their cores, those dense central bulges with the supermassive black holes, they swing by. They pass within tens of thousands of light years, which sounds like a lot, but for galaxies, it's nothing. It's a whisper, and in that moment, gravity turns into something else. It becomes an artist, but an artist of chaos. The pull on the near side of a galaxy versus the far side, that difference becomes extreme. The tidal force peaks. And it does something. It pulls out these long, graceful arcs, stars, gas, dust. They stream out from the main bodies like brilliant ribbons, cosmic ribbons flowing into the void. Astronomers have a name for them, tidal tails. If you could stand on a future Earth and look up, the sky would be completely different. The Milky Way's neat spiral gone. Torn into these luminous streams, Andromeda wouldn't be a faint smudge anymore. It would be a blazing, chaotic swirl, tangled with our own stars. The two galaxies would fill half the sky. Their tidal tails arcing overhead, a silent, slow-motion explosion of light. NASA has run supercomputer simulations of this. They show it with breathtaking clarity. These aren't just guesses, they're calculations, the pure mathematics of gravity rendered into visual poetry. You watch the two disks approach, they swing past. And from their outer edges, great plumes get lifted out, 10,000 stars at a time, gently. They aren't destroyed, they're set adrift, those tails. That's the galaxies losing pieces of themselves. It's the first real mixing, two separate families of stars beginning to blend. This phase is critical. It's the point of no return. The galaxies aren't just passing by. They're exchanging material, they're being stripped. Their original, pristine shapes are coming apart. Their individual identities start to blur. Those graceful spirals that lasted billions of years undone. Undone in a single, graceful gravitational maneuver. It's a prelude, a dramatic opening act, and it ensures the dance can't end with a simple retreat. Their momentum is altered, their paths are forever entwined. They're destined now to swing back around, drawn together for a second encounter, even closer. The merger has truly begun. The tidal tails show this luminous chaos. It looks violent, like a cosmic demolition derby, and that raises the most common question about the merger: what happens to the stars? Will they collide? The answer is no, they almost certainly won't. Think of it as two immense swarms of bees. Each swarm has hundreds of billions of bees. They're flying toward each other across a continental distance, and when they meet, they pass right through. The swarms merge and mingle into this chaotic cloud. But do the individual bees smash into each other? Almost never. The space between each bee is so vast they just fly past. They change direction. They get swept along in new currents. But they don't crash. A galaxy is that swarm. The bees are stars, and the space between them is almost incomprehensibly empty. You can put numbers to that emptiness. In the disk of our Milky Way near our Sun, the average distance between stars is about 4 to 5 light years. That's how far light travels in 4 years. Now take the size of a typical star. Our Sun is a good example. Its diameter is less than 1/1,000,000th of a single light year, so the scale is like this. Picture 2 grains of sand, separate them by about 500 miles, then set them in motion. The chance of those 2 specific grains colliding is effectively 0. That's the reality of galactic structure. Stars are tiny, brilliant pinpricks in an ocean of darkness. During the merger, gravity acts like a giant hand stirring that ocean. It will fling stars onto wild new orbits. It will pull them into those long tidal streams. It will toss stars from what was the Milky Way into what was Andromeda, and the other way around. The stellar populations get thoroughly mixed, but the stars themselves just pass by each other, like ships in an unimaginably vast night. Astrophysicists who model this are very clear. One researcher called it a gravitational rearrangement, not a stellar demolition derby. The forces reshape the distribution of matter. They do it by moving stars along new paths through mostly empty space. Direct collisions between stars are so rare we can consider them impossible. That changes the whole nature of the event. It moves it from destruction into restructuring. A peaceful, if profoundly disruptive, blending. So while the galaxies as organized structures get torn apart, the individual star systems, the individual suns and their planets, they will almost all survive the journey intact. They'll just find themselves in a new neighborhood, under new skies, inside a single, blended galaxy. The real violence, the real source of drama and change, isn't with the stars. It's with something else entirely, the thin gas and dust floating between them. The stars themselves drift past each other, but the gas between them, that thin interstellar medium, the hydrogen and helium clouds, that's where things change. When galaxies meet, that gas doesn't just slip by, it collides, it compresses, and that compression sparks something, a burst of new stars, a stellar baby boom so bright it can outshine the whole galaxy. That's the real spectacle of the merger, this luminous, chaotic rebirth across the sky, and it leads to a question: what happens to us? Where does our solar system go during all this? Supercomputer models give us a forecast, a range of possibilities. In most simulations, our solar system gets moved. It probably won't stay in the spiral arm suburbs. The gravitational tides are too strong, the reshuffling too complete. One likely path, our Sun, with Earth and the planets, gets flung outward, not into empty space, but into one of those long tidal tails. We could become part of that luminous stream of stars cast out into the galactic halo, a remote, quiet place in the new galaxy, or the dance could pull us inward. On a looping path toward the merged galaxy's core, a crowded place, a more hazardous place, the models don't agree on the exact path, but they agree our corner of the cosmos will be unrecognizable. From a future Earth, the sky would tell the story. The Milky Way's familiar band, that river of light, would first warp and stretch, then it would shatter. Replaced by a chaotic tapestry of streams and glowing clouds, Andromeda wouldn't be a faint smudge anymore. Over millions of years, it would grow into a colossal, tilted spiral dominating the night. Then, as the galaxies pass through each other, the two would blend, a single, roiling mass of light. New star clusters, blue-white from the colliding gas, would ignite like diamonds on velvet. The night would never be truly dark again, but will Earth even have a surface to stand on? That's where astronomy meets planetary science. The Sun, in 4 billion years, will still be shining. A main sequence star, but it's slowly getting brighter. Long before the merger's final act, that increased solar energy will likely have made Earth uninhabitable for complex life. The oceans may have boiled away, the atmosphere transformed. Earth's story as a living world as we know it will probably have reached its natural end. The cosmic show overhead would play to an empty theater. That blending of timelines is something. It means the most dramatic event in our galaxy's future might occur in a silent chapter of our planet's history. It frames a certain reflection. We're living in a narrow window, a window where we can look up, understand the slow dance of the giants, and trace the fate of our own tiny world within it. Our solar system's journey through the merger isn't about survival, it's about legacy, our home being moved gently and irrevocably from one chapter of the universe into the next. The violence in a merger isn't about destruction, it's about creation. When two galaxies swing past each other, the gas between the stars can't just slip by. These huge clouds of hydrogen and helium collide. They slam together at incredible speeds, and that collision compresses the gas. It squeezes it. Under that sudden pressure, vast regions of gas reach a point. Gravity takes over and they collapse. They ignite, not in one spot but in thousands of places, millions of places, all across the merging chaos. That's a starburst. A frenzied, galaxy-wide burst of star formation. The universe's most spectacular fireworks. You'd look up at a future night sky. The old constellations are gone, scattered by the tides. In their place, new clusters blaze to life. They look like glowing patches, nebulous stellar nurseries, lit from within by the blue-white light of newborn stars. And many of these new stars are monsters, massive, hot, short-lived. They burn their fuel in just a few million years, shining with an intensity that can outshine our sun 1,000,000 times. Their light floods the galaxy, turning a stately dance of old yellow stars into a riot of sapphire and diamond. We don't have to just imagine it, we can see it happening. Look at the antennae galaxies, a pair of spirals caught in the act of merging about 60 million light-years away. In images, they're a tangled wreck of stars and gas. And right at their hearts, where the gas collides most violently, you see it. Knots of intense, pinkish glow. Those are the starburst regions. Each one is a factory producing thousands of new stars. Hubble has peered into these knots, resolving them into clusters. Some contain more than 1,000,000 stars. That's our preview. A real-time demonstration of what will happen to the Milky Way and Andromeda. This reveals a paradox. An event we call a collision, a crash, is also one of the universe's most potent engines for new life. The merger tears down the old structures. But in doing so, it provides the raw material and the trigger to build anew. It seeds the future galaxy with fresh generations of stars, and with those stars come new possibilities. New protoplanetary disks, new worlds, new chances for the chemistry of life to begin somewhere on some future planet under those new suns. The chaos of the merger isn't an end. It's a violent, brilliant, and necessary rebirth. The starburst is one layer, but at the heart of the chaos there's something else, a slower, more powerful drama. The central black holes of both galaxies are starting their own journey. In the Milky Way's core, there's a quiet giant, Sagittarius, a star, a supermassive black hole, 4 million solar masses. It's relatively dormant, and in Andromeda's heart, its counterpart is even larger, a silent titan, maybe 100 million solar masses or more. For billions of years, they've ruled their separate domains. But the merger changes that. As the galaxies blend, these black holes aren't left behind. They're the most massive single objects in the whole system. And in the crowded, chaotic core of the new galaxy, they feel a strange drag, dynamical friction. They move through a dense sea of stars, and their immense gravity pulls stars toward them, slinging them away on new orbits. Each gravitational slingshot acts like a tiny brake. It robs the black hole of a little momentum. Over millions of years, this friction makes them sink. They spiral down like two heavy stones sinking through water toward the new common center of gravity. They'll eventually find each other, and when they do, they begin a dance. A binary dance. They'll orbit one another, separated by maybe just a few light years. Picture that. Two voids in space, each with the mass of millions of suns whirling around their shared center. A cosmic waltz of pure gravity. This binary phase can last an astonishingly long time, hundreds of millions of years, maybe even a billion, and as they circle, they do something incredible. They ripple the very fabric of space-time itself. They emit gravitational waves. These aren't waves of light or sound. They're literal distortions in the geometry of the universe, moving outward at the speed of light. The whirling black holes lose energy with each orbit, spiraling closer together. Future astronomers, if any exist in that distant era, would witness this through a new kind of science. Multi-messenger astronomy. They might detect the gravitational waves with vast observatories in space. They might also see the surrounding gas, heated to incredible temperatures by the dance, glowing fiercely across the electromagnetic spectrum. They'd piece together the story from multiple signals, waves, and light telling the tale of the final act. And then, finally, they merge. Billions of years after the galaxies first combined, the two black holes coalesce into one. In a fraction of a second, they release a final, titanic burst of gravitational waves, a thump in the cosmic background, a final punctuation mark on the merger event. The new, even more supermassive black hole will then sit at the heart of the blended galaxy, a silent monarch in a new kingdom, a testament to a union that reshaped an entire corner of the cosmos. This new galaxy, they've already named it. Astronomers called it Milkomeda, or sometimes Milkdromeda. It's just a blend of the two names, but naming it does something. It turns a future event into a place, a destination. You can point to it, you can say, that's where our star will be, in Milkomeda, but what will it be like? The science gives us a forecast. The spiral shapes of the Milky Way and Andromeda will be gone. Those spirals exist because of a quiet, ordered rotation. A delicate balance. The merger destroys that balance. The gravitational tides, the mixing of stars from different orbits, it leads to something called violent relaxation. Over hundreds of millions of years, the orbits of billions of stars get scrambled. They're thrown onto new, random paths, no neat circles. The stars move every which way like a swarm. And that swarm settles into a specific shape, not a flat disk, a three-dimensional blob, a football shape, an ellipse. Astronomers call this an elliptical galaxy. That's the likely fate for Milkomeda, a giant elliptical galaxy. From afar, you wouldn't see spiral arms, no dust lanes, just a smooth, glowing ellipsoid of light. An ancient, yellowish light. The color is key. Elliptical galaxies are often called red and dead because the merger's starburst uses up almost all the gas and dust. The material for new stars is gone, so the galaxy is left with its aging stars. The massive blue stars burn out fast. What's left are the longer-lived, cooler, redder stars. The galaxy quiets down. It enters a stable retirement. Cosmologists see this as a natural endpoint. In galaxy groups like ours, mergers are the primary engine of growth. Each merger builds a larger galaxy, often into this elliptical form. It's a standard chapter, so Milkomeda isn't random. It's the next evolutionary step. A mature, settled giant, a cosmic retirement home for hundreds of billions of stars, including our Sun. Giving it a name makes that future tangible. It lets you project forward to a time when the night sky would show the gentle, uniform glow of a single, blended city of stars, a city with a new name built from two ancient ones. We can predict what happens to galaxies with a lot of confidence because we've built universes inside computers. Those details about Milkomeda, the tidal tails, the final elliptical shape, they don't just come from theory. They come from computational astrophysics, where supercomputers act like time machines for the cosmos. Scientists take the laws of physics, the math of gravity, the behavior of dark matter, the dynamics of gas. They translate all that into billions of lines of code. They create a virtual universe. They seed it with conditions that match our own, and then they press play. The simulation runs forward. It calculates the gravitational pull between every virtual particle over billions of years of simulated time. It's an astonishing feat. One of the most famous views of our galactic future came from a NASA team. They didn't model two galaxies as simple blobs. They gave each one a realistic structure. A dense core, a sprawling disk of stars, vast gas reservoirs, and that massive halo of dark matter. They set them on their observed collision course. And then they let the laws of physics determine what happened, nothing else. The result was that now iconic video, the graceful dance, the stretching. The first pass, the eventual merger, it matched what astronomers see in other merging galaxies across the universe. That match is the key. It's how we know the simulation is trustworthy. Scientists use an iterative process. They run a simulation, then they compare its final state to snapshots of real, present-day galaxies. If it doesn't look right, they adjust the initial recipe. The amount of dark matter, the starting speeds, the angles of approach, and they run it again. They repeat this until the virtual universe reliably produces galaxies that look and behave like the ones we see through telescopes. Only then do they have a model they can trust to run far into the future. A lead scientist on one project described it as a constant conversation between prediction and observation. We are not just guessing, we are testing a digital replica of reality against reality itself. The supercomputer becomes a laboratory for cosmic destiny. This process demystifies the predictions. It shows they are not science fiction. They are the logical, calculated outcome of physical laws we understand very well. It showcases the power of turning mathematics into a visual story, allowing us to witness an event that will unfold long after our sun has faded. The simulation shows our specific fate. But to understand it, you have to zoom way out. This merger isn't some accident. It's not a disaster. It's a standard chapter. It's how galaxies grow up. Our own Milky Way isn't some untouched island. It has a history written in its outer halo, a history of consumption. There are these faint, ghostly remains scattered around it. The remains of smaller galaxies it's absorbed over billions of years. We can see their stellar streams, long, arching rivers of stars that were once separate. They've been pulled in, stretched out, digested by the gravity. This process has a name: hierarchical merging, the idea that large structures build themselves from smaller ones. Our galaxy didn't form in isolation. It was assembled piece by piece from countless smaller mergers, and we're not the only ones with a past. Look at Andromeda. Its outer halo is a chaotic graveyard. Hubble surveys have mapped these vast, complex structures of stars around it, the shattered remnants of galaxies it consumed long ago. One of them is called the Giant Stellar Stream, a colossal arc of stars, a fossil of a dwarf galaxy torn apart maybe billions of years ago. Andromeda wears the scars of its own growth. So this upcoming collision isn't a first for either of them. It's the next major acquisition, the biggest one for eons. Both have been the dominant predators in our local group, feeding on smaller neighbors. Now the two giants are turning toward each other. This is the inevitable next step, the final merger that will define the mature form of our corner of the cosmos. To see how common this is, you look back in time. The Hubble Deep Field images, those long exposures peering into the most distant reaches, they show us the early universe. And it's a place of chaos. The galaxies there aren't the neat, orderly spirals we see nearby. They're small, irregular, often caught in the act of colliding, smashing together, triggering furious starbursts. In that young, dense universe, mergers were the primary mode of growth. That's how galaxies were built. That grand narrative frames our local event. The Milky Way Andromeda merger isn't an exception to the rule. It is the rule playing out on a delayed schedule. We live in a relatively quiet suburb of the universe, so the most dramatic phase of our galaxy's growth was postponed, but the underlying process never stopped. Gravity has been working toward this moment since the two galaxies first formed. That perspective changes everything. It moves the event from a singular catastrophe into its proper place. A natural, evolutionary transition. The birth of Milkomeda isn't an ending, it's a maturation, the formation of a larger, more stable structure, following a blueprint the universe has used for over 13 billion years. Our home galaxy has been growing since its birth. Its greatest growth spurt still lies ahead. From the quiet edges of the local group, another pair of eyes could be watching. We've been telling this story from inside the Milky Way, but to really see the scale, you have to step outside, far outside. Picture a view from the Triangulum Galaxy. M33, it's the third largest galaxy in our little group. From there, the coming merger would be a show, a deep sky spectacle, two brilliant spirals. Each one a whirlpool of starlight. They'd slowly come to dominate the view. They wouldn't look like faint smudges, they'd be grand, detailed. An astronomer there would see the Milky Way and Andromeda the way we see Andromeda now, a distinct tilted spiral. Over thousands of years, they'd watch the two giants start to change. The first signs would be subtle, a warping in the spiral arms, a brightening along the edges. Then, as the galaxies made their first close pass, the real spectacle would start. Long, luminous filaments of stars would emerge, the tidal tails, they'd stretch across the void, slowly intertwining like celestial ribbons, a silent, slow-motion ballet of light, playing out across an enormous canvas. From that distant seat, the violence of colliding gas clouds would just be brilliant knots of blue-white light, speckling the merging forms, a breathtaking demonstration of gravity's artistry, visible from millions of light years away. This shift in perspective does something. It frames our galactic story not as a solitary epic, but as one act in a larger play, and it raises a question about the observer. What happens to the Triangulum Galaxy itself? It's not just a passive audience, it's caught in the same gravitational web. Current models suggest a few possible fates. It might be drawn into the merger later, becoming a third ingredient in the Milkomeda mix, further stirring the pot. Or the complex gravitational slingshot from the two giants merging could fling Triangulum away entirely. Ejected from the local group, set adrift into the intergalactic void as a lonely wanderer. Its destiny is tied to the dance of its larger neighbors. This exercise in cosmic empathy is more than a thought experiment. It's a fundamental tool of astronomy. To understand our place, we have to learn to see ourselves from the outside. From that extragalactic viewpoint, the merger loses any hint of catastrophe. It becomes a natural process, even a beautiful one, a process of change. It reminds us that galaxies aren't isolated islands, they're social creatures, constantly interacting, pulling and pushing on one another across the vast spans. Their lives are stories of relationship and gravity. The universe is a theater of constant, slow-motion interaction. Our home galaxy's most defining future chapter will be a shared one, a testament to the fact that nothing exists in true isolation, not even an island of 400 billion stars. The universe is expanding, galaxies are moving apart, but there's one galaxy that's not, Andromeda. Its light isn't stretched out, it's compressed. That compression shifts the light toward blue. A blue shift, that's the signature of something moving toward you. It's like sound. A siren coming toward you has its sound waves squeezed, the pitch goes up. When it moves away, the waves stretch, the pitch drops. That's the Doppler effect. Light does the same thing. If a star or galaxy is coming toward us, its light waves get squeezed. That's a blue shift. If it's moving away, the light stretches. That's a red shift. Astronomers measure this. They use spectrographs. They break the light into a rainbow and read the shift. And the big story of the cosmos, the one Edwin Hubble found, is written in redshift. Almost every galaxy shows it. Their light is stretched, reddened. That tells us space itself is expanding, carrying galaxies apart. Andromeda is the major exception. It's blue shift that tells us something else is happening here in our local group. Against the whole universe expanding, there's a stronger, more local force, gravity. The mutual pull between the Milky Way, Andromeda, all their dark matter. It's so strong it's overcome that expansion. In our neighborhood, gravity has won. That single piece of data, that shift toward blue, was the first real clue. For decades it was a puzzle. Was it just sideways motion or a true approach? Refining that measurement, separating it from our own solar system's motion, took a century. It culminated with the Hubble Space Telescope observations. They confirmed the trajectory. The blue shift wasn't an illusion. It was a measurement of destiny. It proved that while the universe at large flies apart, the largest structures within it are still drawing together, bound by gravity, this counter current in the cosmic river. That's what makes our future certain, the birth of Milkomeda. The blue shift of Andromeda is our local story, but these galaxies aren't solitary. They each have a court of smaller attendants. The Milky Way has its own entourage. The most famous are the large and small Magellanic Clouds. You can see them from southern skies, two fuzzy patches. They're dwarf galaxies caught in a long orbit around ours, and Andromeda has its own collection, maybe even more of them. So when the giants merge, what happens to their courts? It adds a layer of complexity. Think of two royal families, each with children and servants, coming together. The children don't just stand still, they get swept up. Some might be torn from their parents' side, others might be adopted into the new household. For the dwarf galaxies orbiting us, the merger is a gravitational hurricane. Their stable orbits are shattered. Supercomputer simulations show this. As the two large galaxies swing past, their gravity acts like a pair of giant hands stirring the space around them. Some of the smaller satellites get caught in a gravitational slingshot. They're flung away at incredible speeds, ejected from the local group entirely. They become intergalactic wanderers set adrift in the dark voids between clusters. Their light would fade as they journey into isolation. Other dwarfs suffer a different fate. They might be drawn in earlier. As the galactic cores pass close, tidal forces can strip a dwarf galaxy apart. Its stars are pulled out into long streams. They contribute to the growing stellar halo of the new combined galaxy. It's a gentle destruction. The dwarf loses its identity. Its stars become just part of the background population of Milkomeda. And some might survive the initial passes only to be absorbed later. As the new elliptical galaxy forms and settles, its gravitational reach extends. Any remaining satellites will slowly, over billions more years, spiral in and be assimilated. Their stars will join the great, smooth halo. This is hierarchical merging in microcosm, playing out faster. So the merger isn't a simple, clean, binary event. It's the reorganization of an entire galactic family. A dozen or more smaller galaxies, each with its own history, will have their destinies rewritten. Their stars will be scattered, their gas stripped away, their paths forever altered. They become the raw material for Milkomeda's extended halo. So when we look at those faint clouds, the Magellanic Clouds, we're not just looking at neighbors. We're looking at fellow travelers on this long journey. Their fate is intertwined with ours, subject to the same gravitational forces. Their story reminds us that galaxies aren't isolated. They exist in ecosystems, in families, where the actions of the largest members dictate the lives of the smallest. The birth of Milkomeda will be a messy, glorious reunification of an entire cosmic clan. The stars pass by peacefully. That's only half of it. The real violence happens between them, in that thin ocean of gas and dust, the interstellar medium. It's the raw material for new stars. It fills a galaxy like a ghostly atmosphere, and when the Milky Way and Andromeda swing past each other, their two atmospheres don't slip by. They slam together at hundreds of kilometers per second. That creates a shock wave, a cosmic sonic boom on a galactic scale. This collision of gases is direct and violent. It compresses clouds in an instant. It heats huge regions to millions of degrees, so hot they don't glow in visible light. They glow in X-rays. If you could see that future sky in X-rays, you'd see a web of brilliant filaments. Arcs of million-degree plasma tracing the outlines of the colliding atmospheres. We've seen this in other mergers, the mice galaxies. Their long tails are connected by a bridge of this superheated, X-ray emitting gas. It's a signature of the chaos between the stars. This turbulence does two things. First, it triggers starbursts. The shock waves rip through cooler hydrogen clouds. They squeeze them so violently the clouds collapse. Thousands of new stars ignite at once. Second, this violent mixing heats up so much gas that it never cools down to form stars. It gets blown out into the galactic halo, or it swirls into the core, feeding the central black holes. That's why elliptical galaxies, like Milkomeda will be, end up with so little gas left. The merger uses it up in a final burst of creation. Then it blows the rest away, so the collision is a story of two scales. The stellar scale is stately, gentle. The gaseous scale is a turbulent, fiery forge. It shows a galaxy isn't one thing. It's a multi-phase ecosystem. And when two ecosystems merge, their most delicate components, their atmospheres, collide with ferocious energy. They light up the universe in invisible light, and in doing that, they write the final chapter on star formation for the new galaxy they're building. That first close pass isn't the end, it's the start of something much longer. The galaxies swing by each other, but they don't crash. They have too much momentum. They swing apart again, like two pendulums brushing past each other. They fly out to a great distance, slowed by gravity, and then they stop. Gravity pulls them back. They fall toward each other a second time. That's the start of a long orbital decay, a multi-pass waltz that could last over 1 billion years. Each time they come together, something happens. They transfer energy and angular momentum, but to what? They're not solid objects. The transfer happens through a subtle process. As the dense cores move through each other's halos of dark matter and stars, they create a wake. A gravitational wake, like a boat moving through water. The boat leaves a turbulent trail, and that turbulence saps its forward motion. For the galaxies, the wake is made of stars and dark matter particles getting slung around. Each slingshot steals a tiny bit of energy from their orbital motion. That's dynamical friction, gravity's braking system on a cosmic scale. The effect is cumulative. With each pass, the galaxies come back a little slower. Their maximum separation gets a little smaller. Their orbits become tighter, more circular. They spiral inward. The beautiful chaos of the first pass gives way to a more stately inspiral. The two distinct cores, each with its own supermassive black hole, begin to orbit a shared center of gravity. Like a binary star system of unimaginable scale, you can see a simpler version in a physics classroom. two pendulums, hang them separately, and they swing independently. But if you connect them with a weak spring, or place them close enough that their motions influence each other through the air, they become coupled. The energy of one transfers to the other. Their individual swings become erratic, then they eventually synchronize, swinging together as one system. The galaxies are like those pendulums. The spring is gravity itself, mediated by all the invisible mass in their halos. They are becoming coupled. Their separate rhythms are entraining, synchronizing on a path toward a single beat. This slow march toward equilibrium is the final act. It's not a violent collision, but a gradual relaxation. The wild orbits of stars stirred up by the first encounters will, over hundreds of millions of years, settle down. The galaxy finds a new shape that reflects its scrambled state. That shape is the smooth football of an elliptical galaxy, a state of rest, a new equilibrium born from a billion years of gravitational negotiation. The dance doesn't end with a crash. It ends with a slow, graceful settling as the last echoes of the two original spirals fade into the calm of a single, blended home. The sky during that starburst would be sapphire and diamond, but that brilliance is fleeting. Those massive blue stars, they're the rock stars of the cosmos. They live fast, they die young, burning through their fuel in just a few million years. Their final act is a supernova, a titanic explosion, and that explosion seeds the surrounding space with heavy elements. The elements that make planets and life possible, but after the flash, they're gone. What's left are the quieter stars, stars like our sun, and stars even smaller and cooler. These stars are frugal. They burn for billions of years, trillions even. They shine with a steady light, golden or reddish. As the merger progresses over eons, this natural cycle plays out on a galactic scale. The frenzied starbursts use up the last great reservoirs of gas, so no new blue giants are born to replace the ones that explode, and the overall color of the galaxy begins to shift. It cools, it reddens, the cosmic palette changes. If you could watch for a billion years, the merged Milkomeda won't be the blue and white whirlpool we see in spiral galaxies today. It'll become a smooth, golden amber ellipsoid. Astronomers call this the red sequence. Elliptical galaxies dominate it. They're galaxies where star formation has essentially ended. They're in retirement. Their light is the combined glow of countless ancient suns. This connects the life of a single star to the destiny of a galaxy. The brief, spectacular burst of youth gives way to a long, stable adulthood. The color tells the story. A reddish galaxy is an old galaxy, a galaxy whose most dramatic days of creation are in its past. So the future night sky from a planet in Milkomeda wouldn't be dark. It would be bathed in a soft, uniform, reddish-golden glow, a gentle light from hundreds of billions of senior stars. A permanent twilight from suns born long before the merger even began. It's a peaceful, if solemn, cosmic sunset, the final brushstroke on a canvas 13 billion years in the making. The last part of the merger isn't written in light. It's written in the geometry of space. Two supermassive black holes spiraling together, they're in this binary dance. And they generate gravitational waves. Think of a still pond. The surface is smooth. That's like undisturbed space-time. You drop a stone, ripples spread out from the impact. They warp the surface. A heavier stone moving faster makes bigger ripples. Now imagine two stones whirling around each other in the water before they sink and merge. The ripples they make are complex, powerful, and they travel outward across the whole pond. Gravitational waves are those ripples, but in the fabric of the cosmos. They're not made of light or matter. They are literal stretches and squeezes in space itself. As the black holes orbit, they warp the space around them. And those warping effects move outward at the speed of light. The frequency of the waves is tied to the orbital speed. In the final moments before the merger, the waves become a rapid chirp. rising in pitch and strength. For the Milky Way and Andromeda merger, this final chirp will be at an extremely low frequency, too low for ground-based detectors. Like LIGO is tuned for higher frequencies, from smaller black holes and neutron stars. To hear the finale of our galactic story, we need to listen from a place free of Earth's noise. The future is with space-based observatories, like the proposed Laser Interferometer Space Antenna, LISA. That mission would use 3 spacecraft, flying in a giant triangle millions of kilometers apart, using lasers to measure minute distortions in space-time as the waves pass by. It would be like a microphone for the universe's deepest vibrations, a future chapter in astronomy. Where we monitor the cosmos through a new sense, we could hear the final moment of the Milkomeda merger, long after the light show of colliding gas has faded into that golden, elliptical glow. A direct detection of an event set in motion billions of years ago, a testament to gravity's power to shape not just matter, but the very stage the universe plays out on. It's a coincidence of timing, really our ability to see this future. We happen to live in a specific window, a brief one, where the night sky tells a clear story. We can still see the Milky Way as a spiral. We can pick out Andromeda separate, approaching. We have the physics, the tools, the right vantage point to trace their paths billions of years forward. And that's not a small thing, it's a feature of this moment. Now, imagine the alternative, a civilization that emerges in Milkomeda tens of billions of years from now. Their sky would just be a single, smooth glow, an elliptical haze, the 2 spirals gone, merged, scrambled for them. Figuring out where their galaxy came from would be like archaeology. They'd have to dig for clues in the motions of old stars, the narrative we see so clearly, written right across the sky for them, that'd be a faded mystery. And that connects to something broader, sometimes called the anthropic principle, which just says, our observations are filtered by the fact we're here to make them. We can only exist and ask these questions in an era that allows it. We're on a planet around a stable star, in a galaxy that's made the heavy elements for life. During a time when the universe is transparent enough, structured enough to be understood. This moment is golden for cosmic archaeology. We're late enough that the universe has cooled into galaxies we can map. And we're early enough that those galaxies still have their original shapes. Their histories are still legible. We're positioned perfectly to watch the prelude to one of the universe's great processes, galactic mergers. We're not at the beginning, we're not at the end, we're in the middle where the plot is clear. It makes you reflect. Our species on this tiny world emerged at just the right time to look up and comprehend not just where we came from, but where we're going. We can trace stars being born from earlier ashes. We can see the wreckage of past small mergers in our galactic halo, and we can forecast the next great merger with real precision. That knowledge is a gift of this epoch, a temporary privilege. It frames a humbling truth. Our curiosity is matched by a cosmic context that lets us satisfy it. We're in a brief chapter where the universe is both old enough to be interesting and young enough to still be understood. Our window to see the spiral giants poised for their dance. It won't last forever. But for now, we can watch, we can calculate, and we can appreciate the luck, the extraordinary luck of being here now to witness the setup for a drama that will unfold long after we're gone. We know the galaxies will collide, that part is certain, but the details, the exact way it happens, those aren't locked in yet. Our predictions have a margin of error. There's still room for the unknown. One of the biggest unknowns is something called tangential motion. We know Andromeda is moving toward us, but is it coming straight on, or does it have a sideways drift? If you see a car coming right at you, you can predict the collision. But if that car is also sliding to the side, even a little, everything changes. The impact becomes a glancing blow. The point of contact shifts. For Andromeda, that sideways motion is incredibly hard to measure from here. It's a tiny angle across a huge distance, but it makes all the difference for how the first pass unfolds. Then there's the dark matter, the invisible halos around both galaxies. Our models make assumptions about their shape, their density. But if the dark matter is clumpier than we think or more spread out, that changes the gravitational forces. It changes how the galaxies stretch during the close approach. It changes the tides, so our understanding isn't fixed. It's a working model. New data comes in and we adjust. The Gaia mission is doing that now. It's not looking at Andromeda. It's mapping over 1 billion stars in our own galaxy with incredible precision. By knowing our own galaxy's mass and motion in detail, we can better isolate Andromeda's true movement. We can pin down that sideways drift. Every new piece of data from Gaia, from future telescopes, it adjusts the supercomputer simulations. The timeline of 4 billion years might move. By a few 100 million years forward or back, the tidal tails might form at a different angle. That's the process. It's a strength. Science is a conversation. We update the map as we get better charts. We're not proclaiming an unalterable fate. We're giving the best forecast we can, while acknowledging the cosmos might still have surprises. That honesty doesn't weaken the prediction. It builds trust in the method that will keep clarifying our future right up until it becomes the present. Our local group has more than 2 giants. There's a third spiral, smaller but still significant, the Triangulum Galaxy, M33. For a long time, people thought its role in the Great Merger would be minor. A distant spectator, but new data has changed that. It now looks like Triangulum isn't just passing by. It's probably gravitationally bound to Andromeda. A satellite in a huge, slow orbit, and that changes everything. It puts a third major body into the gravitational equation. The classic 2-body problem of our merger becomes a chaotic 3-body dance. That adds layers of suspense to the forecast. The future of Milkomeda might not be a simple binary blend. It could be a triple merger. Simulations that include Triangulum show complex possibilities. One scenario is dramatic. As Andromeda and the Milky Way make their first close pass, their immense gravity could slingshot Triangulum onto a new path. A path that sends it plowing through the outer disk of the Milky Way, long before the main merger finishes. This wouldn't be a galaxy-wide collision. Stars would still pass by harmlessly, but the interstellar gas clouds they would collide. That would trigger a separate, earlier starburst in our galaxy's outskirts. A preview of the main event. Another possibility is gentler but just as final. The tidal forces from the 2 giants could simply tear Triangulum apart. Its stars stripped away into long streams, its identity lost. It would become just another set of ribbons in the grand tidal tapestry of the merger. Its gas would be consumed, fueling more star formation in the blended mess. These competing scenarios show a crucial truth. The local group is a dynamic, interacting system, not a static collection of islands. The gravity of each member influences all the others in a complex web that unfolds over cosmic time. Pinpointing Triangulum's exact fate is an active area of research. It requires more precise measurements of its motion and more sophisticated supercomputer models. Models that can handle the gravitational chaos of 3 large spirals. This ongoing discovery shows that even the future of our own galactic neighborhood isn't fully written. There are chapters still being drafted. The potential involvement of a third galaxy adds an element of unpredictability. It reminds us that the cosmos isn't a clockwork mechanism. It's a living, evolving network of relationships, and our place within it is part of that beautiful, dynamic complexity. Milkomeda's final shape will be a smooth, golden ellipse. That's the story it tells, but the stars inside it, they tell a different one, a much older story. Long after the merger's visible signs are gone, its history stays. Written in the motion and the chemistry of billions of suns, that's galactic archaeology. It's how we uncover a galaxy's past, not by digging, by reading the sky. Every star is a fossil. It carries two things from its birth, its motion and its chemical makeup. The motion is an imprint. It comes from the gravitational place where the star was born. The chemistry, what astronomers call metallicity, is a record of the gas cloud that made it. Stars born together in the same place and time, they share a family resemblance. In their speed, their direction, their elemental makeup, we do this detective work here in our own Milky Way. With missions like Gaia mapping stars, we've found ghostly rivers. Stellar streams, they're the shredded remains of small galaxies. Ones our Milky Way consumed billions of years ago. Their stars move together on similar, distinct paths. Like a school of fish against a current, and they often have a different chemical signature, lower in heavy elements, compared to stars born in the Milky Way's main disk. They're immigrants and we can identify them. Now take that, project it forward to Milkomeda 10 billion years from now. The two grand spirals are gone, blended into one smooth glow. But for a future astronomer with advanced tools, the blend isn't perfect. Deep in that elliptical haze, there will be patterns. Subtle ones, vast, diffuse populations of stars, their orbits ever so slightly aligned, stars with a specific range of metallicities, clustering together in velocity space. These will be the ghostly remains of the Milky Way's disk and Andromeda's disk. They'll be thoroughly mixed in position, but their origins, they'll still be legible. In their dynamics, in their chemistry, it would be a monumental puzzle, like finding two colors of sand, perfectly mixed in a giant hourglass, and then, grain by grain, separating them. Based on subtle differences in weight and shape, that future scientist would have to disentangle the populations. Statistically, they might identify one large group of stars with orbital characteristics that suggest they once belonged to a massive, fast-rotating disk. That would be the Andromeda progenitor. Another group, slightly different, might trace back to a smaller disk, perhaps more metal-rich, the remains of the Milky Way. They might even find the faint, stretched-out trails, the great tidal tails, now relaxed but still detectable as over-densities in certain orbital paths, the merger's most dramatic moments frozen in the orbital ballet of its stars. This reframes the whole event. The collision that creates Milkomeda isn't an erasure, it's an encoding. It takes two separate histories and weaves them into a single, complex archive. The violence of the merger doesn't destroy the past, it scrambles it into a new form. One a sufficiently clever observer could still decipher. The future galaxy becomes a cosmic palimpsest, an ancient manuscript where the original writing, though overwritten, can still be seen beneath the surface. The story of two cities becomes a single, layered text, waiting for a reader in the distant future. The final part of the Milkomeda story starts in silence. After all those bright flashes fade, the galaxy settles into a long, quiet autumn. There's no gas left to make new stars. The engine of creation has run out of fuel, so what's left is a galaxy of ghosts and embers. The main light will come from red dwarf stars. Small, miserly stars glowing with a faint red light for trillions of years. The bigger stars, like our Sun, they've already burned through their fuel. They shed their outer layers, and what's left behind is an Earth-sized core of white-hot carbon and oxygen, a white dwarf. These stellar cinders will cool over eons, fading from white to yellow to red and finally to cold black diamonds just drifting in the dark. The most massive stars ended as supernovas. They left behind neutron stars, city-sized spheres of unbelievably dense matter, or stellar black holes. And at the very center of the galaxy, the merged supermassive black hole just sits there, quiet and dark, having consumed everything it could reach. This is the galaxy's retirement. A calm, steady dimming, a collective sigh after all the drama of its birth and merger. The sky from any surviving world would be a tapestry of faint red points, and the occasional sharp blue-white pinpoint of a cooling white dwarf. The great blended glow of Milkomeda itself would slowly redden and dim. This quiet autumn stretches into a cosmic winter. And you have to pull the camera back further to the scale of the whole universe. Galaxies like Milkomeda aren't isolated. Their fate is tied to everything. What we see now points to a broad, sobering path. The universe keeps expanding, and that expansion seems to be accelerating, driven by this mysterious force called dark energy. In one possible future, that acceleration never stops. Galaxies become more isolated. The space between them stretches so much that, from any one galaxy, all the others eventually redshift out of view. They vanish beyond an invisible horizon. The universe becomes a collection of isolated islands, each one growing darker and colder. Inside each island galaxy, star formation ends. Stars burn out. Black holes might slowly evaporate over incomprehensible timescales through Hawking radiation. Matter itself could decay. What remains is a near-perfect vacuum, filled only with a faint, uniform bath of radiation, cooled to almost absolute zero. That's the theoretical heat death, not a fiery explosion, but a slow, eternal fading into equilibrium. A state of maximum entropy where no energy is left to do work or to create or to change. It's the ultimate quiet. Other theories suggest more dramatic ends. If dark energy grows stronger over time, it could lead to a big rip, where the accelerating expansion becomes so fierce it overcomes all binding forces. Not just between galaxies, but within them. Gravity would be defeated. First, Milkomeda would be torn apart, then solar systems, then planets, then atoms. The fabric of spacetime itself would be shredded. A far more violent but equally final punctuation mark. These are visions of an almost meaningless future. Timescales so vast they dwarf the entire multi-billion-year saga of the Milky Way and Andromeda merging. That merger, which feels like the defining event of our galactic future, becomes just a brief flash. A single, vivid chapter in a story that continues for trillions upon trillions of years. It's a profound perspective shift. Our home galaxy's great collision and rebirth isn't an ending. It's a transitional phase, a step in a much longer journey from the structured, energetic universe of today toward a far simpler, colder, and quieter one. That knowledge doesn't diminish the merger's grandeur. It frames it. It highlights the precious, dynamic era we happen to live in. We live in the cosmic springtime. An age of light and structure, of galaxies colliding and stars being born. An age where the narrative is still being written in fire and gravity. The heat death is a shadow on the far horizon, so distant it has no power over the stories unfolding now. It just reminds us that all things, even galaxies, have seasons, and we are here, remarkably, in the season of greatest spectacle, able to trace the arc of our own galactic story. From its assembled past through its coming merger and far, far beyond into the deep quiet of time. That future, deep time, cosmic quiet, that's a vision from physics. But the merger itself, the process, you can picture it through something simpler. Think of two very large parks, mostly empty grass, but with a few thousand people scattered in small groups. These parks aren't still. They're on a gentle, invisible conveyor moving toward each other across a flat plain. The people are the stars, the parks themselves, the land and the air. That's the dark matter halo. That's the real structure, the space that holds everything. As they drift closer, the people inside don't feel alarmed. They're so spread out that from any one person's view, the other park is just a distant blur. They keep their casual strolls. The parks finally meet. They don't crash. They begin to pass through each other. And here's the key: the people, the stars, they almost never bump. They just weave through the gaps, nodding politely as they pass strangers from the other park. But the parks themselves, their shape changes completely. The force of the interaction stretches them. It pulls long, thin peninsulas of grass and trees out from the edges. Some people find themselves walking out onto these strange new pathways far from the main crowd. That's the tidal force. It distorts the container, not the contents. The two crowds become thoroughly mixed. You can't tell who started in which park anymore. They're all just people in one big, chaotic, blended space. Now imagine there are organizers in this scene. They have bullhorns. They represent gravity. At first, their instructions seem chaotic, just adding to the noise. But over a very long time, their calls become more coordinated. They don't tell each person exactly where to go. Instead, they create a new collective rhythm. Slowly, patiently, they guide the entire mingled crowd. The stretched peninsulas of grass are drawn back in. The chaotic milling settles. Everyone is gradually corralled into a single, new, circular park. A park with no distinctive features, where people walk in every direction, not in neat streams. That's dynamical relaxation leading to an elliptical galaxy. The organizers with bullhorns didn't force a new structure. They allowed the crowd to find a new equilibrium, a calm after the energetic mixing. In this simple analogy, you have the whole saga. The dark matter halos as the true, massive parks, the stars as sparse individuals who rarely meet, the tidal forces that stretch the galaxies into streams. The eventual gravitational settling into a smooth, blended shape. It takes a process spanning billions of years and reduces it to a human-scale metaphor, a crowd merging in a city square. It shows the cosmic isn't always incomprehensible. Sometimes it's just a very, very slow version of patterns we recognize right here. The starbursts will create new solar systems. Out of that chaos, countless ones, within those glowing clouds where gas is colliding, gravity will pull together fresh protostellar disks around infant stars. And those disks are where planets form. They're the raw material, so the merger isn't just mixing old stars, it's manufacturing potential for new planetary families. On a colossal scale, each starburst region becomes a factory for future Earths or Jupiters or worlds we can't yet imagine. The chemistry will be rich. It's seeded by heavy elements from earlier generations of stars, stars that lived and died in both galaxies. So this event, which reshapes the large structure, also sows seeds for new small worlds in the darkness around new suns, creation and destruction. They're two sides of the same coin. The violent collision of galactic atmospheres becomes the gentle cradle for planets. And if life requires certain conditions, then this merger, in its fiery forge, might be creating billions of new chances for it to begin somewhere under a new star. In the distant future of Milkomeda, but the planets that already exist, our solar system will likely survive the stellar dance, so will countless others. Around stable stars in both the Milky Way and Andromeda, the gravitational mixing means these established systems won't stay put in their original neighborhoods. A star born in Andromeda with its own retinue of planets could be flung into a region that was once the heart of the Milky Way. The populations will blend. A future astronomer born in the Milky Way's remnants could study a planetary system, one that originated in another galaxy entirely, and the very concept of an extragalactic planet, a world from beyond our galaxy, would become meaningless. Inside Milkomeda, they would all simply be planets, citizens of a new, unified realm that sparks a thought. Consider the sheer diversity of worlds that might be stirred together. Planets formed from the slightly different chemical soup of Andromeda, worlds orbiting stars of different ages and different types than are common here. Imagine the variety of geology, of atmospheres, of potential histories. The merger creates a cosmic melting pot, not just of stars, but of entire planetary legacies. And it raises a question, a tantalizing one currently unanswerable. If life or intelligence exists on some of those worlds, the merger would bring those separate threads of biological or cultural history into the same galactic sphere for the first time. They would share a future under the same golden, elliptical sky. Now, directly detecting such planets, especially small rocky ones, across such vast distances, that remains a monumental challenge, far beyond our current technology. We struggle to image planets clearly in our own galactic neighborhood, but the merger creates the conditions where the search for a sufficiently advanced civilization within Milkomeda becomes a unified internal census. They wouldn't need to look to other galaxies to find alien worlds. They would be living among them, woven into the very fabric of their blended home. So the Great Merger is more than a restructuring of light and mass. It's a unification of possibilities, a gathering of distant shores into a single, shared ocean, waiting for future explorers to map its countless hidden worlds. This knowledge about our galactic future, it's a kind of mirror. It shows us something about ourselves. For thousands of years, we looked up at the stars and we told stories. The Milky Way was a river of light, a path for spirits, the spilled milk of a goddess. Those were human-scale stories. They put us at the center of a meaningful world. Then science moved that center. We learned the Earth goes around the sun. That sun is one of billions in a galaxy, and that galaxy itself is temporary. It's going to merge and it's going to fade. That can feel like a story of erasure. Like we've been demoted from the center of everything to a temporary speck in a cosmos that doesn't care. That feeling has a name: cosmic insignificance. It's the vertigo of scale, the realization that all of human history, everything we've done, is less than a blink in the life of a galaxy. But that same feeling has a counterweight. A deep cosmic connection, because we are the part of the universe that became conscious. We can look out, trace the light from Andromeda, run the equations, and understand this grand future. The atoms in our bodies were forged in stars, stars that lived and died long before our solar system even existed. We are stardust that has woken up. And we're using that stardust to understand the dance of the galaxies it came from. This isn't just observation, it's a kind of kinship, a recognition that we aren't separate from the cosmos. We are its growing edge of self-awareness, so this prediction does something unique. It doesn't just tell us where we are, it tells us where home is going. And in doing that, it asks us a question. What does it mean to care about a future so distant that no human language will probably survive to name it? For some, the answer is a renewed focus on our fragile present, on preserving this pale blue dot, our only certain home for the foreseeable future. For others, it sparks a drive to make sure something of us endures. Our curiosity, our stories, our knowledge, to cast a kind of cultural message in a bottle into the deep time of Milkomeda. This is the legacy impulse. It's why we build archives, why we send probes beyond the solar system, why we point telescopes at the future. We are trying to speak across that abyss of time. Not to the inhabitants of that future galaxy who may never exist, but to the universe itself, to say, we were here, we saw this, we understood. This turns astronomy from a passive study into an active act of meaning-making. It becomes the story we tell ourselves about where we belong in the unfolding epic of space and time. The merger of the Milky Way and Andromeda is a physical fact. But our knowing of it, our tracing of its billion-year arc, that's a human achievement. It's our small, brave way of making the cosmos feel less like a void, and more like a home with a history we can read and a future we can glimpse. A Voyager probe, if we sent one out now, would still be out there when the galaxies finally meet. They're built to last, those spacecraft. Their power sources will die in a few hundred years, but the probes themselves, the actual structure, they're hardened. They could drift for millions of years, maybe billions. They're the most durable things we've ever sent out, but over that kind of time, even they face erosion. Micrometeorites, radiation, the chance one survives untouched to pass through the center of the new galaxy, that chance is incredibly small, but it's not zero. It's a quiet idea, a human object seeing that future dawn. We could try for something more secure, a time capsule buried deep in the rock of a dead moon. Titan maybe, or in a vault on our own moon, but then you have to think about the sun. The sun will become a red giant. It will swallow the inner planets. Could a capsule survive that? Maybe, if it's far enough out, but it would also have to survive the merger itself, the gravitational chaos, orbits shifting. New bombardments, it's an engineering problem, but across billions of years, which shows you something. Any physical thing we make, it's subject to the same erosion. The same forces as a mountain. Entropy gets everything in the end. So the thing that might actually survive, it isn't metal, it isn't a disk, it's the knowledge. The understanding, gravity, stellar evolution, how galaxies move, the map we've made of the future, that map isn't in one place, it's a pattern. It could be kept by a culture that lasts longer than Earth. It could be in a library on a world around a red dwarf star, a star that burns for trillions of years, or it could just be the logic of the universe itself, waiting in the structure of things for anyone later on who learns to see it. So the legacy isn't the object, it's the observation, not the golden record, but the fact we learned to listen. To read the blue shift of Andromeda and understand what it meant, we took a brief moment of consciousness and used it to draw a line of understanding across this huge span of time. That act connects us, our short chapter, to the galaxy's long story. It means even if every city on Earth is dust long before the merger starts, the story we found, the story of two spirals becoming one, that becomes part of the cosmic narrative. Because it's true, and truth, once it's known, has a kind of permanence. It waits in the equations, in the starlight, for anyone who learns to look. That grand story, written in starlight, has also been written in stories. Science fiction has looked at Andromeda and seen a canvas, a place for adventure, for survival, for destiny. Long before supercomputers gave us a forecast, writers were imagining the moment our galaxies meet. In classic novels, the merger is a looming deadline, a cosmic event that makes civilizations act. Sometimes it's a threat, a wave of destruction moving toward inhabited worlds. Other times it's a mystery, a profound astronomical puzzle to solve. The timescale of billions of years is almost always compressed. For a story to work, the collision has to happen in a time frame characters can witness, or at least prepare for within a few generations. That's a creative liberty, but it serves a purpose. It brings an event of unimaginable slowness into a human-scale narrative. It lets us feel the weight of it. The dangers are often exaggerated too. In these stories, stars don't just drift past each other, they collide. Planetary systems are shattered. It's a spectacle of pure cosmic violence, and that makes for compelling drama. It turns the merger from a slow gravitational dance into an immediate, visceral crisis. A test for any civilization caught in the middle. But even in these dramatized versions, the core truth often remains. The merger is presented as inevitable. A force of nature so vast that no technology can stop it, only perhaps survive it, so the story shifts. It's not about preventing the event, it's about responding to it. It becomes a tale of adaptation, or of unity, or a desperate search for a new home. These narratives explore what it means to be a fleeting, conscious species in a universe of immense, impersonal power. Modern films and series have used the concept too, sometimes as a breathtaking visual backdrop, a sky filled with two colliding galaxies, not as a distant forecast but as the present reality. That imagery does something powerful. It makes the abstract concrete. It gives viewers a visceral, emotional sense of scale, a sense of wonder that a graph or a simulation might not. It plants the idea in the public imagination. This bridge between rigorous science and popular culture is vital. The precise, patient work of astronomers provides the raw material. The compelling, emotional work of storytellers takes that material and makes it resonate. One gives us the facts of our future, the other helps us feel what those facts might mean. And together, they ensure a discovery locked in equations doesn't stay there. It becomes part of our shared mythology, a new chapter in the ancient practice of looking at the night sky and telling a story about our place within it. These fictional explorations, for all their creative liberties, serve the same goal as the science: to pull our gaze upward, to expand our sense of time and possibility, and to remind us we are part of a narrative far grander than our own. The map of our galactic future, it wasn't drawn by one hand or one nation. It's a collective thing. It's what happens when human curiosity points the same way. This forecast, this billion-year prediction, it's made from threads of data from telescopes and instruments all over the globe. Operated by teams that speak dozens of languages, but they share one goal. You have to consider the precision. To know Andromeda is coming toward us, we first had to know exactly how the stars in our own galaxy are moving. That task fell to the European Space Agency's Gaia mission. For years, that spacecraft has been doing the most detailed stellar census ever, measuring the positions and motions of over 1 billion stars in the Milky Way. It's a map of unprecedented accuracy. By understanding our own galaxy's dance, we can subtract its motion, isolate the true trajectory of Andromeda against the cosmic backdrop. Gaia's data is a gift to the world. Its catalogs are free, available to astronomers everywhere, fueling thousands of studies. That data gets combined with observations from other great observatories. The Hubble Space Telescope, an international project of NASA and the European Space Agency, it provided the critical long-term monitoring, watching stars within Andromeda itself, confirming its sideways motion. In the future, the James Webb Space Telescope, with its deep infrared vision, will peer into the hearts of other merging galaxies, giving us clearer templates to compare against our models. These aren't American or European instruments, they're humanity's eyes on the cosmos. And then there are the supercomputers, the simulations that show the merger unfolding. They run on some of the most powerful machines on Earth. In facilities from Japan to Germany to the United States, they crunch numbers that would take a desktop computer millions of years, turning the cold math of gravity into a visual story we can all understand. A scientist in Chile might write the code using data from a European satellite to run on a supercomputer in Texas, all to answer a question that belongs to every person on the planet. The voices behind this work reflect that. An astrophysicist might say we are all made of stardust, and now we're using that stardust to understand the fate of the galaxies that forged us. A project scientist for a major telescope might say this isn't just about predicting a collision. It's about understanding the life cycle of the universe and our tiny, wonderful place within it. These aren't competitive claims, they're shared reflections on a shared journey. That collaborative spirit frames the pursuit of knowledge as one of our most unifying projects. In a world often divided, the silent, patient work of understanding the cosmos continues. It asks questions that transcend borders. Where did we come from? What is our place in all of this? And where are we going, literally and figuratively? The quest to map the future of the Milky Way, and Andromeda gives an answer. A profound, if silent, one. We are going there together as a species clever enough to look ahead and united enough to chart the course. Looking at this future is like looking into a distant mirror. And it shows us something about right now. The timeline is huge, almost impossible to grasp, but the meaning isn't stuck out there in that far-off time. It matters today. It matters because it stretches what we think time even is. Knowing our galaxy will merge, that's not just future gazing, it's a key. It unlocks things about the cosmos we live in right now. Studying this event, this thing that will happen, it forces questions. Questions about dark matter, that invisible stuff holding everything together. It makes us refine our ideas about gravity itself. We start to see galactic mergers differently, not as rare catastrophes, but as the standard engine. The way growth happens across cosmic history, that knowledge, it changes our map of reality. It tells us the serene spirals we see, those beautiful pinwheels in telescopes, they're temporary. They're just arrangements in a universe of constant, slow-motion change. That's a profound insight, and it came from centuries of human curiosity. That curiosity is the real point. Our ability to make this prediction, it's a staggering achievement. Think of the chain, ancient people looking up, naming a faint smudge, then the telescope. Then the painstaking measurement of starlight, observatories launched into space, digital universes built inside supercomputers. This forecast is a monument to the human drive to understand. It's countless people across generations, across cultures, each adding one piece of data, one equation, one line of code. We took our brief moment of consciousness and we drew a line of understanding across billions of years. That act, it's worthy of awe, not for its scale, but for what it says about us, about what we can do when we look up, when we ask questions together. And this perspective, once you have it, it changes how you see your own time. It provides a humbling context for the challenges of our era. Against the backdrop of galactic time, our current conflicts, our anxieties, they're placed in a different light. That doesn't diminish them, it frames them within a grander narrative. It encourages a long-term view of our species' potential. If we can project the fate of galaxies, what could we achieve here on Earth? If we applied that same foresight, that same cooperation to the stewardship of our own planet, the merger becomes a metaphor for interconnection, for inevitable change. It urges us to think in terms of legacy, what we leave for the generations that will inherit this world, long before the stars begin to blend. So why care about an event 4 billion years away? Because the story isn't really about that collision, it's about seeing it coming. It's about the perspective that knowledge gives us right now. This cosmic forecast is a gift of context. It pulls us out of the narrow confines of daily life. It places us inside an epic story, a story of construction and change and continuity. It reminds us we are participants in a universe that is knowable, that is dynamic, that is breathtakingly beautiful. The true value of mapping this merger, it's not in the distant future it describes. It's in the wisdom it offers us today, under our own still separate sky. We started with a faint smudge in the night sky, and we ended with a golden, elliptical galaxy. That journey covered billions of years. We traced the pull of dark matter. We watched the gravitational dance, and we saw that a galactic collision isn't about destruction. It's about transformation. The stars will weave past each other in the dark. The gas will ignite, and two great spirals will become one. This knowledge gives us perspective. It puts our brief human moment inside a story of almost unimaginable scale. We're here now, in this narrow window. The night sky still tells two separate stories. The river of the Milky Way and the approaching glow of Andromeda. We're here in the time between the construction of the spirals and their eventual union. We're living in the prologue to one of the universe's great acts of creation. It expands our sense of home. Our home isn't just this planet or this solar system. It's this galaxy, and by extension the entire local group, caught in a shared gravitational destiny. The atoms that form us were forged in stars, stars that lived and died in this galactic neighborhood long ago. We are, in a literal sense, the local universe becoming conscious of itself, and with that consciousness we can look ahead. We can map the future of the very structures that gave us life. So this knowledge shouldn't make us feel small. It should make us feel connected. It should be a source of wonder, not anxiety. The universe isn't a cold, empty void. It's a dynamic, evolving tapestry, and we have the privilege of being the part that can look at the tapestry and begin to understand its pattern. We can see the threads being woven. Even the threads that won't be joined for eons. Our story is a tiny, vibrant stitch in that grand design, but it's a stitch that sees, a stitch that questions. A stitch that can trace the outline of the whole. That's a beautiful and humbling truth. It invites us to look up at the night sky with new eyes, not as a static backdrop, but as a page in a story still being written, a story where we play a fleeting but wonderfully aware part.